Okay, on page 46 of your table of contents, please write exponential functions. Exponential functions, page 46. Remember, we filled in with the word problems on 44 and 45. And then we will flip to page 46. Exponential functions. Okay, so exponential functions, it says it right in the name, exponent, right? Exponential functions, if we define that, are a function, and remember function is a fancy word for equation, where the independent variable, so the variable independent, the one that's not going to change, it's not our answer, it's what we put into the problem, the independent variable, which is the variable x, right? We put numbers in for x and solve for y, so the independent variable x is an exponent. So let's talk examples. An example of that would be f of x equals, now remember f of x is the same thing as y equals, this is just function notation. And if we did 2 times 3 to the x power. So my independent variable, what I put into the problem, my x value, is an exponent. So this equation maybe represents, let's give this a reason, why are we solving this? This represents the number of insects after x days. So this formula, this exponential function, this equation, if I substitute 1 in for x for 1 day, it'll tell me how many insects will be in the population. If I insert 2, 3, so on, it will give me the value, the number of insects after x days. Remember that when you're doing these types of problems, you need to use order of operations. So you need to do your parentheses first, but inside our parentheses there's nothing to do. Then we move to our exponent, so we're going to do 3 to the x power, and then we're going to multiply. 3 to the x power, get a solution, and then we're going to multiply by 2. So let's solve for after 5 days. So after 5 days, and my x value, because my x value here is 5, my x value is 5. So I'm going to do the function of 5 is 2 times 243, because 3 to the 5th power is 243. Again, I do my exponent first, parentheses, there's nothing inside the parentheses to do, so I move to my exponent, 3 to the 5th power. And then lastly, I'm going to multiply. So the function of 5, after 5 days, there will be 486 insects. So identifying, right? Identify is a fairly low-level Bloom's idea. Identifying is just looking and seeing. Is this an exponential function? Is your variable an exponent? If your variable is an exponent, yes, it is an exponential function. Or you could be given a set of values. If you're given a set of values like negative 1, 1.5, and then the next set of values is 0, 3, 1, 6, and 2, 12. Right, so this could be given to you as ordered pairs, or it could be given to you in a table. Let's put it in a table so we can see both. Right, our domains and our ranges. Domains are your x values, so negative 1, 1.5. Remember to put your x values in order. then 0, 3, 1, 6, and 2, 16. So we look to see if it's linear, right? If it's linear, we look to see is there a common addition or subtraction in our y values. If it's linear, a linear equation has a common y value, addition, or subtraction. So if I look, let's say from 3 to 6, I add 3, but 6 plus 3 does not equal 16. So this is not a linear equation. So now I'm going to check to see, is it exponential? If it's exponential, there's a common y value of multiplication or division. And I can already see that I made a mistake in copying this. I'm going to change that 16 to a 12 to make this work. So multiplication or division. So let's look. So from 6 to 12, what do? I multiply by 2. From 3 to 6, I multiply by 2. And 1.5 times 2 does equal 3. So there is a common y value of multiplication or division. So I get to the next y value by multiplying. And just double check. Is this +1, +1, +1? So this works. This is, yes, exponential. So again, just to recap, yes, it's exponential. Why is it exponential? Why is this set of values exponential? The x values are addition or subtraction, and the y values are multiplication or division. So then we're going to talk about graphing. Is it an exponential when graphing? So you're going to get a graph, glue it down at the bottom. So let's just graph this function on here to show what an exponential function looks like. So at -1, 1.5, 0, 3, 1, 6, and 2, 12. So an exponential graph in a graph form, it needs to curve. It's going to get big fast, right? So it's going to get really big really fast. So if they're asking you to pick values to substitute, you should substitute +(-1), 0, +(-2). If you get bigger than 2 sometimes, it's not going to fit on one of these graphs. Unless they provide you a graph that has pretty big values, you're going to get really big really fast. I mean, because when we substituted the x value of 2 into this equation, we were already off the graph. So you're going to have to be a little artistic when you're curving that graph. So let's recap. If you're given an equation, how do you know that an equation is an exponential function? The x value is an exponent. How do you know if a set of ordered pairs, a relation, is an exponential function, your x values have the same common, right? Addition or subtraction still in our x values, but your y value needs to have multiplication or division, a common multiplication or division. And if it does have a common multiplication or division, then you're good to go. It is exponential. If it does times 2 times 2 times 4, but over here it's 1, 1, and 1, that's not going to work. It could be times 2 times 2 times 4 if this was plus 1 plus 1 plus 2. So you have to look for common ratios. Right? Are these equivalent fractions all the way down your table or your set of ordered pairs? And then if you're given a graph, is it an exponential function? It needs to make a curve. It could open up, it could go up to the right, or it could go down to the right. It could be upside down. It could be any of those things as long as it has a curve. There is no straight line in an exponential function.